This is the Cretaceous-Paleogene boundary. The KPG line. It is not an abstract concept. It is not a theoretical date in a textbook. It is a physical horizon you can reach out and touch. It cuts across continents. Visible in cliffsides from New Zealand to North Dakota. When we trace a finger across this line, the world changes. Below it, the rock holds the heavy bones of massive dinosaurs, the coiled shells of marine ammonites, and the fossilized pollen of complex, sun-drenched forests. Above it, there is an immediate, deafening biological silence. Late Cretaceous, about 66 million years ago, to understand how a stable, highly specialized biosphere collapses so completely, we cannot rely on imagination. We must read the forensic signature left inside the stone itself. In 1980, geologists were attempting to measure the exact deposition rate of that thin dark clay. They wanted to know how long it took to form. Instead, they found something that did not belong on the surface of the Earth. The boundary layer was spiked with an extreme concentration of iridium. Iridium is a dense, silvery white metal. It is exceedingly rare in Earth's crust, having sunk toward the planet's core during its early, molten formation. But it is abundant in asteroids. Embedded alongside this extraterrestrial metal were layers of soot, the chemical signature of immense wildfires, and grains of shocked quartz. These quartz crystals had been fractured along rigid, parallel planes by a sudden, immense pressure wave, a force that far exceeds normal tectonic activity. The rock record preserves a distinct boundary, proving that a massive extraterrestrial body struck the planet, leaving a global chemical fingerprint in a matter of hours. SRC-01, Alvarez, L. W. et al. 1980. But knowing that an asteroid hit the planet is not the same as understanding how it dismantled a global food chain. An explosion, even on a planetary scale, is a localized event. The initial shockwave, the thermal radiation, and the towering tsunamis would have devastated everything within a few thousand kilometers of the impact site. But physical trauma alone does not explain why species on the opposite side of the globe, living in completely isolated ecosystems, died out at the exact same moment in geologic time. The answer to that paradox lies in the specific, tragic chemistry of the rock the asteroid happened to strike. The impact crater is known as Chicxulub. It spans roughly 180 kilometers across the Yucatan Peninsula and the shallow waters of the Gulf of Mexico. Today, it is buried under tens of millions of years of subsequent sediment, completely invisible from the surface. For decades, its exact dimensions could only be mapped indirectly through gravity anomalies, measuring subtle shifts in the density of the Earth's crust from above. To read the actual mechanics of the impact, and to finally understand the mechanism of the extinction, we had to go down into the crater itself. In the spring of 2016, an ocean drilling platform positioned itself off the coast of Mexico. It held its coordinates directly over the buried peak ring of the Chicxulub crater. A peak ring is the circular ridge of mountains that forms inside a massive impact crater when the Earth's crust rebounds violently. In the seconds following the strike, the solid rock briefly acted like a liquid drop, splashing upward before freezing into jagged peaks. A heavy drill pipe descended through the warm waters of the Gulf, grinding through the seabed and hundreds of meters of Cenozoic limestone. It was seeking the specific rock that was fractured on the very day of the impact. This work is highly physical, methodical, and slow. Cylinders of rock, the drill cores, are pulled to the surface, laid out in long plastic troughs, and split perfectly down the middle. Researchers log the color, the density, and the mineral composition of every millimeter. When the drill finally reached the impact horizon, the core revealed a chaotic, melted breccia. This was rock subjected to pressures and temperatures so extreme that it behaved like a fluid before rapidly freezing back into solid stone. But what was missing from the core was far more important than what was preserved. The Yucatan platform is built on deep layers of carbonate rock and evaporites. Specifically, the region is rich in anhydrite, a mineral packed with calcium and sulfur. Yet, in the melted rock pulled from the peak ring, there was a stark void. The pressure of the strike was so immense that these specific rock layers were not merely shattered or melted. They were vaporized. A core taken from the Chicxulub peak ring reveals dozens of meters of melted rock deposited in a single day. But a glaring absence of sulfur-rich evaporites, proving they were vaporized into the stratosphere. SRC02, Gulick, S.P. et al. 2019. This missing rock is the physical constraint that rewrites our understanding of the extinction. The asteroid did not just hit the Earth, it struck a massive, concentrated reserve of sulfur. When billions of tons of vaporized sulfur are ejected into the upper atmosphere, they react with water vapor to form sulfuric acid aerosols. These microscopic droplets do not fall back to the surface immediately. Suspended in the stratosphere, far above the weather systems and rain clouds that could wash them out, they spread rapidly, driven by high-altitude winds. They wrapped around the entire globe. Sulfur aerosols are highly reflective. As this chemical veil enclosed the planet, it acted as a global mirror, bouncing incoming solar radiation back into deep space. From the surface, the sky would have darkened, taking on a bruised, twilight quality even at noon. Without the heat of the sun penetrating the atmosphere, global temperatures plunged rapidly, initiating a sudden, brutal impact winter. But far more devastating than the sudden freeze was the loss of light. Photosynthesis requires a continuous, reliable input of solar energy to convert carbon dioxide into the organic compounds that sustain life. When the sulfur veil blocked the sun, that energy pipeline was severed. The impact winter was not just a season of extreme cold, it was the sudden, mechanical shutdown of the planet's primary producers. The blast radius determined what burned, but the chemistry of the vaporized rock determined what starved. Under the bright, sterile lights of a laboratory fume hood, a paleontologist carefully pours hydrofluoric acid into a plastic beaker. Inside the beaker is a crushed sample of gray shale, pulled from the layer of rock sitting immediately above the KPG boundary line. Hydrofluoric acid is highly corrosive, capable of dissolving solid silicate rock. But it leaves behind something incredibly resilient, the microscopic, organic outer walls of pollen grains and plant spores. When this dark organic residue is washed, centrifuged, and mounted on a glass slide, the microscope reveals a hidden landscape. To understand the shutdown of photosynthesis, we do not need to rely on the rare preservation of fossilized leaves. We can simply count the microscopic reproductive cells that blanketed the ancient soil. Samples taken from the limestone just below the KPG boundary are crowded with diverse shapes. Looking through the lens, researchers log the heavily textured spheres of flowering plants and the winged grains of ancient conifers. Together, they represent a dense, sunlit Cretaceous forest. But in the samples taken from the barren shale immediately above the iridium layer, that diversity vanishes. As the slide is systematically scanned under the microscope, the researcher clicks a mechanical counter. Instead of dozens of distinct plant species, a single shape dominates the field of view. These are the simple, uniform spores of ferns. Ferns possess a unique ecological advantage. They do not rely on insects or birds for pollination, and their spores can travel vast distances on the wind, settling and sprouting in highly degraded, nutrient-poor soils. They are the first colonizers of modern volcanic flows, and the first green shoots to emerge after a devastating forest fire. Immediately above the boundary line, fossil pollen records show a sudden drop in complex plant diversity, with up to 90% of the microfossils consisting of spores from pioneer ferns. SRC03, Voider, V. et al. 2001. This fern spike is not just a botanical curiosity. It is the visual proof of a total food web collapse. When the sulfur veil blocked the sun, the complex forests died back. The massive herbivorous dinosaurs, adapted to process hundreds of kilograms of fresh vegetation a day, were biological engines that could not be idled. When the primary producers disappeared, the herbivores quickly exhausted their fat reserves and starved. Without the herbivores, the apex carnivores soon followed. The impact winter dismantled the ecosystem from the bottom up. To find out what made it through the darkness, we open the heavy steel drawers of a museum collection. These cabinets house fossils from the early Paleocene, the epoch immediately following the extinction. A fossilized jawbone rests on a foam pad. It belongs to an early mammal, and it is not much larger than a fingernail. The cold metal jaws of digital calipers slide shut across a fossilized molar, registering a measurement of only a few millimeters. The exact duration of the impact winter remains an area of active debate among climate modelers. But the physical dimensions of these bones prove the deep freeze lasted long enough to act as a ruthless metabolic filter. We cannot reconstruct the exact daily movements of these early mammals, but the physical dimensions of their bones place a hard limit on their biology. Their extreme small size meant their absolute caloric requirements were fractionally low. Instead of relying on fresh vegetation or large prey, they could sustain themselves on the grim surplus of a dying world. They fed on roots, seeds buried deep in the soil, insects breaking down decaying wood, and the carrion of much larger animals. This forces a shift in how we view the history of life. The survivors were not inherently smarter, faster, or more highly evolved than the dinosaurs they replaced. Mammals did not win a biological war. They simply passed through a brutal taphonomic and metabolic filter. Extreme small size and a generalist, scavenging diet shifted from being marginal traits to absolute survival imperatives. Eventually, the sulfur aerosols agglomerated and washed out of the stratosphere as acid rain. The skies slowly cleared, and sunlight touched the surface of the earth once again. The pioneer ferns gradually gave way to returning shrubs, and over hundreds of thousands of years, complex forests took root in the ash. But the giants that had pruned those forests for tens of millions of years were gone. The survivors were tiny, emerging from their burrows into an unfamiliar, empty landscape. As the earth began to warm, the strict constraints of the impact winter were lifted, and evolution was handed a blank slate. Paleocene epoch, about 58 million years ago, deep in the Cenozoic coal mines of northern Colombia, heavy excavators tear away layers of dark, carbon-rich rock. They are digging to reach the commercial coal seams below. This coal is the compressed, fossilized remains of one of the first dense tropical rainforests to emerge after the asteroid impact. The environment was a humid, swampy basin, heavily flooded by slow-moving rivers. The acidic, waterlogged conditions of a peat swamp are highly destructive to bone, meaning preservation bias heavily filters what survives here. Most animals that died in these waters simply dissolved. But occasionally, a massive bone was buried deep enough in the anoxic mud to mineralize and turn to stone. A paleontological field crew works quickly behind the mining equipment. They scan the newly exposed rock, looking for the dull shine of fossilized bone against the black matrix. From the dark rock, they extract a single, massive vertebra. It is heavy, dense, and instantly recognizable as belonging to a snake. But the scale of the bone defies the known limits of modern biology. In a lab, this fossilized vertebra is placed on a padded table beside the vertebra of a modern green anaconda, one of the largest and heaviest snakes alive today. The anaconda bone is roughly the size of a coin. The fossil vertebra is larger than a human fist. To determine the size of the animal this bone supported, researchers rely on allometric scaling. Allometry is the mathematical study of how the size of one specific body part, in this case, the central weight-bearing core of a vertebra, changes in strict proportion to the overall length of the animal. A researcher uses digital calipers to take precise measurements of the fossil's width and height. These numbers are then plotted onto a graph. mapping the exact dimensions of modern boid snakes against their known body lengths. The resulting calculation is staggering. Based on the strict geometric scaling of living boid snakes, a vertebra of this diameter suggests an animal over 12 meters long, weighing more than a metric ton. SRC04, Head. J. Et al. 2009. This is Titanoboa cherryginensis. The discovery of a 13-meter snake is not just a biological novelty. It places a profound constraint on our understanding of ancient climates. We cannot put a thermometer into the Paleocene air. But Titanoboa acts as a living gauge of the planet's thermodynamic state. Snakes are poikilotherms. They are cold-blooded. They do not generate significant internal body heat through a high resting metabolism the way mammals or birds do. Instead, their metabolic rate and their ability to grow are strictly governed by the ambient temperature of their environment. In the modern world, the largest snakes live exclusively near the equator, where consistent heat allows them to maintain a high enough internal temperature to digest large prey and support significant bulk. As you move away from the tropics and average temperatures drop, the maximum size of cold-blooded animals shrinks accordingly. This physiological limit means that a snake's maximum potential size is locked directly to the planet's thermostat. By mapping the body size and ambient temperature requirements of modern equatorial snakes, and projecting that line outward to match the immense bulk of Titanoboa, researchers can calculate the minimum heat required to keep such an animal alive. Based on this metabolic math, Titanoboa's massive size implies an equatorial climate significantly warmer than today, pushing well above 30 degrees Celsius on average. This specific temperature calculation remains an area of active debate. Some physiologists argue that the scaling of snake metabolism to ambient heat may not be perfectly linear at such extreme sizes, suggesting the Paleocene might have been slightly cooler than the initial models proposed. But the broader pattern is undeniable. Titanoboa could only exist in a profound hothouse environment. This extreme heat is confirmed by a secondary line of evidence. From the same coal seams in Cenozoic, paleobotanists extract fossilized leaves. By measuring the density of stomata, microscopic pores used for gas exchange, and examining the smooth edges of the leaves, they reconstruct a dense, hyperhumid rainforest. It thrived under levels of atmospheric carbon dioxide far higher than the modern era. This reconstruction forces us to reframe our understanding of the animals that followed the dinosaurs. Evolution in the Paleocene was not driving toward monsters for the sake of predatory dominance. The massive size of Titanoboa was permitted, and demanded, by an overheated Earth. The extreme climate provided hyperabundant biomass and the ambient thermal energy required to sustain a massive, slow-burning metabolism. As the Cenozoic progressed, the Earth would experience periods of even more extreme greenhouse warming, peaking in a violent spike in global temperatures known as the Paleocene thermal maximum. But this hothouse would not last. The planet's climate is a restless machine, and the animals optimized for the sweltering heat of the early Cenozoic were about to face a slow, grinding shift in the rules of survival. To track how the Earth's climate shifted after the extreme hothouse of the early Cenozoic, we must leave the coal mines and look to the bottom of the ocean. In a geochemistry lab, a researcher places a petri dish under a microscope. Dispersed across the glass are grains of deep-sea sediment, extracted from cores drilled far into the ocean floor. Using a fine, damp brush, the researcher carefully isolates tiny, spiraling shells, none larger than a grain of sand. These are benthic foraminifera. They are single-celled marine organisms that live their entire lives in the deep ocean. As they grow, they construct their microscopic shells by pulling calcium and oxygen directly from the surrounding seawater. When they die, they sink into the mud, trapping the chemical signature of that ancient water within their calcium carbonate shells. They are not fossils of bone, they are fossils of the ocean's chemistry. The researcher loads these isolated shells into a small glass vial. which is then fed into a highly sensitive machine called a mass spectrometer. Inside the machine, the shells are dissolved in acid, releasing carbon dioxide gas. The spectrometer analyzes the weight of the oxygen atoms in that gas, specifically calculating the ratio of two different isotopes, oxygen-16 and the slightly heavier oxygen-18. This procedure relies on a strict physical law of evaporation. Because oxygen-16 is lighter, water molecules containing it evaporate more easily from the ocean's surface. During a warm period, this evaporated water falls as rain and eventually flows back into the sea, keeping the ratio of the two isotopes relatively stable. But when the global climate cools, that moisture falls as snow at the poles and becomes locked in massive, advancing ice sheets. As the lighter oxygen-16 is trapped in glacial ice, the remaining ocean water becomes increasingly concentrated with the heavier oxygen-18. Therefore, when the mass spectrometer detects a high ratio of oxygen-18 in the shells of benthic foraminifera, it is direct proof that massive ice sheets were growing on land, and the deep ocean was freezing cold. There is a risk of diagenesis, the chemical alteration of these shells by groundwater over millions of years, but by sampling thousands of cores globally, geochemists can filter out anomalies and build a reliable consensus. When millions of these microscopic isotopic readings, taken from sediment cores spanning the globe, are plotted onto a single graph, a profound pattern emerges. This graph is the Zachos curve. It maps the baseline climate of the entire Cenozoic era. On the screen, a jagged line traces the deep history of Earth's temperature. At the far left, shortly after the asteroid impact, the line spikes upward into the red. This visualizes the extreme heat of the Paleocene and Eocene hothouse, the world that supported giants like Titanoboa. But as the line moves right, tracing the passage of tens of millions of years, it does not remain stable. Instead, the Zachos curve shows a long-term cooling trend, plunging jaggedly downward from the Eocene, through the Oligocene and Miocene, and finally crashing into the deep blue of the Pleistocene icehouse. Oxygen-18 isotopes in marine microfossils shift dramatically, proving that the Earth's baseline climate was not a stable paradise, but a highly volatile machine. SRC06, Zachos, J. et al. 2001. This single graph fundamentally reframes the history of life. The animals of the Cenozoic were not evolving on a static stage. Every jag in the line represents a massive shift in ocean currents, atmospheric carbon, and sea levels. As the line plunges toward colder temperatures, the dense, humid forests of the early Cenozoic begin to die back, unable to tolerate the drying air. In their place, vast, open grasslands expand across the continents. When the landscape changes, the rules of biomechanics change with it. The dense jungle ambush tactics of a massive cold-blooded predator are useless on an open, cooling plain. To understand how predators adapted to this shifting, cooling world, we must look at how regional isolation forced biology to extremes. Miocene epoch, about 15 million years ago, as the Zachos curve continues its jagged plunge downward, the global climate cools and dries. But changing temperatures are not the only tectonic force restructuring the biosphere. The slow, relentless drift of the continents fundamentally alters how species interact. South America breaks away from Antarctica and drifts northward, becoming an isolated island continent. For tens of millions of years, it is entirely cut off from the rest of the world. In this isolation, the familiar mammalian carnivores evolving in North America and Eurasia, the early ancestors of wolves, bears, and big cats, are entirely absent. This geographical constraint leaves the apex predatory niche completely empty. But an ecosystem does not tolerate a vacuum. In a museum collection of South American fossils, a massive skull rests on a specialized steel mount. It is nearly the size of a horse's head, but it belongs to a bird. This is the skull of a phorusracid. commonly known as a terror bird. Examining the skull reveals heavy, solidly fused bones in the upper beak, ending in a sharp, downward curving hook. But to understand how this animal hunted on the expanding Miocene grasslands, we must look at its legs. The skeletal mount reveals legs that are drastically elongated and robust. The toe structure is simplified, minimizing contact with the ground. These are not the legs of an ambush predator hiding in dense forest, these are highly cursorial adaptations, built for sustained, high-speed running on open plains, without the evolutionary pressure of competing mammalian carnivores. Flightless birds optimized their biomechanics to dominate the open ground, relying on speed and the structural rigidity of their massive beaks to dispatch prey, while the isolation of continents drove unique terrestrial adaptations. The cooling climate was also restructuring the oceans. As global temperatures dropped, cold, nutrient-dense waters upwelled from the deep ocean. This fueled massive blooms of plankton, which in turn supported the evolution of the first truly gigantic, filter-feeding whales. And as the prey grew immense, the predators were forced to scale with them. From Pliocene marine deposits around the world, isolated teeth are routinely extracted. They are heavy, triangular blades, often measuring over 15 centimeters in length, with distinctly serrated edges. They belong to Otodus Megalodon, because sharks have skeletons made of cartilage, which decays rapidly and rarely fossilizes. We cannot know the exact, complete body shape of Megalodon. The reconstruction of a massive, scaled-up great white shark is a model-dependent assumption. The living animal may have had a very different, perhaps stockier, profile. But while the cartilage is lost, the teeth, and the mechanical limits they impose, are preserved. To understand the absolute limits of this predator, researchers do not rely on speculation. They use finite element analysis, or FAIR. This is a digital engineering tool originally designed to test the structural integrity of bridges and aircraft wings by simulating how materials deform under stress. In a lab, a 3D model of a reconstructed megalodon jaw is loaded into the FAIR software. Researchers apply digital pressure to the teeth, simulating the force required to drive a 15 cm serrated blade through dense bone. The resulting digital stress map lights up in bright reds and yellows, visualizing the immense mechanical load the jaws could withstand. The math is absolute. Biomechanical models suggest bite forces capable of crushing the skull of a large whale in a single strike, defining the mechanical limits of an apex marine predator. SRC05, Rowe, S. et al. 2008. This is confirmed by direct evidence from the fossil record. Whale bones recovered from the Pliocene show deep, parallel gouges that perfectly match the serration patterns of megalodon teeth. But this extreme biomechanical power comes with a severe vulnerability. An animal with a bite force designed to crush whales requires a massive, continuous intake of high-calorie blubber to sustain its immense bulk. As the Zachow's curve continues to drop toward the freezing point, sea levels will fall, ocean currents will shift, and the migration routes of those whales will change. Size and power are not absolute advantages. In a cooling world, they are highly specific adaptations that require constant, massive caloric support. When the Earth finally plunges into the deep freeze, extreme bulk will no longer be an offensive weapon. It will become a desperate biological shield. Pleistocene epoch, about 2.5 million years ago. On the screen, the Zachow's curve drops sharply into the blue, signaling the onset of the Pleistocene glaciations. The planet enters a relentless, grinding cycle. Massive ice sheets advance across the northern hemisphere, scouring bedrock and locking up the oceans. Then, they briefly retreat, only to surge forward again. The Earth is locked in a deep freeze. In the southern hemisphere, this global cooling drives profound aridity. Out on the dry, wind-swept plains of South America, an excavation team works carefully around a massive plaster jacket. The jacket protects the fossilized pelvis of Megatherium, a giant ground sloth. When the heavy bone is finally prepped in the lab and assembled onto a steel skeletal mound, the sheer physical volume of the animal becomes clear. Megatherium was roughly the size of a modern elephant, weighing several tons. Examining the skeletal structure reveals distinct biomechanical constraints. The pelvic bones are massively thickened, flaring outward to support an immense gut. The hindlimbs are heavily robust, acting like biological pillars. This specific architecture indicates that Megatherium was capable of a tripodal stance. By using its heavy tail and thick back legs, the animal could stand upright, reaching high into the sparse, freezing canopy of the dry Pleistocene environment to strip away vegetation. But to understand why a sloth, or a relative of the armadillo, or a relative of the elephant needed to grow to such immense proportions during an ice age, we must look beyond predator defense. The massive bulk of Pleistocene megafauna is often interpreted simply as heavy armor against fierce carnivores. However, when we apply the strict principles of thermodynamics to the fossil record, an entirely different survival strategy emerges. This strategy is known as Bergmann's rule. It is an eco-geographical principle stating that within a broadly distributed group of animals, species of larger size are found in colder environments, while smaller species are found in warmer regions. The math behind this is tied strictly to geometry. As an animal grows larger, its overall volume increases much faster than its surface area. In a freezing Pleistocene landscape, retaining body heat is a constant, brutal battle. A small animal has a high ratio of skin exposed to the freezing air compared to its internal volume. It loses heat very quickly, meaning it must constantly consume high-quality, energy-dense food just to avoid freezing to death. But an animal the size of Megatherium, or a mammoth, or the giant marsupial Diprotodon, has a massive internal volume relative to its skin surface. It acts as a biological furnace. In the Pleistocene, extreme size meant the ability to retain heat, turning sheer bulk into a thermodynamic shield against the ice. This massive volume also accommodated a massive digestive tract. It allowed these animals to process huge quantities of tough, low-nutrient, freezing vegetation that smaller animals simply could not survive on. This reframes how we view the megafauna. They were not invincible monsters designed to dominate the landscape, they were metabolic engines, adapting to the brutal cold of the Ice Age. Their extreme bulk was a highly specialized, expensive adaptation demanded by the specific thermal realities of the Pleistocene, but this extreme specialization created a profound vulnerability. A thermodynamic shield requires an immense, continuous supply of calories to maintain. The megafauna were perfectly tuned to the specific rhythms of the glacial and interglacial cycles. They were massive, heavily armored, and structurally rigid in their biological demands. If that climate rhythm were to suddenly break, or if the environment were to change faster than their slow generation times could accommodate, their massive size would instantly shift from a survival advantage to a fatal liability. And into this world of heavily armored, highly specialized giants walked an animal that possessed an entirely different strategy for survival. In a paleontology lab, a delicate fossil rests on a protective foam ring. It is a cranium belonging to Homo habilis, an early hominin from the Pleistocene of East Africa. When a researcher uses digital calipers to measure the internal volume of the brain case, the tool registers a slight, yet significant, expansion compared to earlier primates. But when you look at the skull as a physical object, what is most striking is its profound fragility, compared to the massive, thick-boned megafauna dominating the Pleistocene landscape. Homo habilis appears helplessly outmatched. The skull is thin. There are no heavy crests for anchoring massive jaw muscles. There are no sharp, elongated canines for shearing meat. And no thick armor plating. The skeleton lacks the sheer bulk required to retain heat efficiently in a freezing world. It lacks the biomechanical leverage to sprint fast enough to escape a specialized apex predator. Biologically, early hominins were marginal, highly vulnerable generalists, but resting on the steel table next to the skull is a piece of direct evidence that fundamentally shifts the balance of power. It is a crude piece of stone, chipped deliberately along one edge to form a sharp ridge. This is an old Auanlithic flake. To understand the consequence of this simple stone, we must look at the fossilized bones of the megafauna found alongside it. Under a microscope, researchers examine the surface of a Pleistocene herbivore bone. The high-powered lens reveals deep, V-shaped grooves cutting across the grain of the fossil. These are not the rounded, U-shaped punctures left by the teeth of a large carnivore. They are not the random scratches of scavengers. They are the deliberate, repetitive cut marks made by a sharp stone edge. This microscopic evidence proves that hominins were accessing a resource physically locked away from them. Lacking the massive jaw strength of a hyena or a saber-toothed cat, a hominin could not shatter a thick femur with its teeth to reach the nutrient-dense marrow inside. But by using a stone hammer and an old Auan flake, they could bypass their biological limits. Stone tools allowed early hominins to extract high-quality calories, compensating for their biological weakness and lack of specialized anatomy. This is the ultimate reframe of the episode. Evolution does not demand extreme size or biological armor as the only path to survival. The megafauna survived the Pleistocene by internalizing their adaptations. They grew massive guts to process low-quality forage, and thick bones to support their bulk. Hominins externalized their adaptations by using tools to process food outside of their bodies. They kept their anatomy generalized and their caloric requirements relatively low. Behavioral flexibility is lighter and faster than biological armor. When the Zachos curve begins its final, rapid upward jag, signaling the end of the deep Pleistocene glaciations, the climate shifts with brutal speed. The ice sheets retreat, sea levels rise, and the vast, open grasslands transition quickly into dense forests or arid deserts. The megafauna, evolutionarily locked into their massive thermodynamic shields, cannot adapt their slow-growing, high-calorie biology fast enough to survive the changing flora, combined with the increasingly efficient hunting pressures of advanced hominins. The giants collapse, leaving behind only the fragmented bones we pull from the permafrost and tar. We survive today not because we were biologically superior, or because we evolved to be the ultimate apex predators. We survive because we remained fragile enough to be flexible. We do not carry the armor of the Ice Age on our bones, we carry the ability to adapt our behavior to a planet that has never stopped changing. The Zachos curve ends at the present day. But the line has not stopped moving. Earth remains a restless machine. And the absolute limits of life are still dictated by the thermodynamic realities of the rock beneath our feet, and the air above our heads.